Okay, hello, and thank you for this opportunity. I am Mohsen Seyit Kazmi Erdebili, a postdoctoral researcher at University of Bologna, Department of the Electrical, Electronic and Information Engineering. I am joining this meeting with my colleague Sebastiano. First, about the University of Bologna, it is it's the oldest university or one of the oldest university in Western world. But on the other hand, it is one of the European leaders in modern technology and science. Within DECICE, which is a 13 Partners Horizon European Consortium, we from University of Bologna contribute expertise across high-performance computing system, cloud edge system, computing continuum, energy efficiency, and AI-driven analytics. About the DECICE, the goal of the DECICE, I can say the goal is to build a open portable management framework that optimize application across HPC, cloud, edge, and IoT environments. It does this by integrating innovative solutions like digital twin, AI scheduler, and many other subcomponents. This comprehensive approach addresses challenges related to system heterogeneity, data locality, performance optimization, and energy constraints in a real-world deployment, especially for edge devices. The role of the University of Bologna in this size, we focus on a work package 2, where we lead the design and implementation of the digital twin. The digital twin is act as a project data intelligence backbone. It ingests and harmonizes monitoring data, exposes structured API, integrates time series databases and machine learning modules for forecasting different metrics. And at the end, it provides the current system state to the AI scheduler and other subcomponent of the DECICE project. And also in work package 2, we have MLOps. We developed a machine learning. We designed and developed a machine learning operation, which hosts all the AI tools. Beyond the work package 2, we contribute in work package 5, especially in use case 3, the drone-based emergency response scenario, where this size is validated under realistic constraints like bandwidth, energy availability, and dynamic mission need. Use case 3 demonstrate how the digital twin, AI scheduler, and in general this size support in the field intelligence by deciding what to process at the edge while offloading some load to the cloud and HPC while maintaining the performance and efficiency. So in summary, I can say that the University of Bologna contribute in work package 2, digital twin, MLOps, and in work package 3, especially in use case, work package 5, sorry, in a use case 3, drone operation.
I'm Sebastiano Mengozzi, and I'm a PhD student at the University of Bologna. A distinctive aspect of our use case is enabling the coordination among geographically distributed computing units. And drones, for example, are deployed in the field. Edge devices acting as off-board base stations are in the field too, and cloud infrastructure hosted in remote clusters and data center. And to achieve this, we rely on robot operating system, also called ROS2. And this is a widely adopted framework for building and coordinating robotic systems. And ROS2 provides scheduling, communication, and orchestration primitives for robotic applications. But traditionally, ROS2 operates within a local area network. And instead, we abstracted the local area network by leveraging VPN combined with Cilium, and which provides a secure and scalable network and service connectivity. And doing this, we enable the coordination across heterogeneous and geographically distributed computing units. And furthermore, ROS2 is containerized inside Docker, and which allowed workloads to be dynamically deployed and orchestrated by the DECICE scheduler across computing continuum. Well, when intelligence data is collected from the field, machine learning models are executed to extract actionable insight necessary to guide and ensure the mission success. And by considering both the operational environment, such as the terrain, the weather, and the status of the platform, for example, the remaining battery life of drones and their position in the field, the system can dynamically reconfigure missions. And this adaptability ensures that mission planning and execution remain optimized, and even in evolving or adverse conditions. This allows the platform to react in real time to external constraints.
Okay. Security in DECICE has at least two dimensions: platform security and data protection. Data protection and privacy, where personal data may appear. We apply different techniques like anonymization. We have already implemented anonymization in another use case of this size, not use case 3, so it's outside of today's DECICE. So I focus mainly on the platform security. We have a different layer in the platform, so we can apply security in the different layers. Like first in a Kubernetes layer, we have a different namespace isolation. We have a role-based access, pod security, image signing, scanning. So we apply different level of the security in the Kubernetes. Then we have another layer, networking layer. We use a Cilium. We apply the different network policy and also security in layer 3, layer 7. So the networking layer has a lot of potential to apply the different security scenario. After that, we have a digital twin. We expose, for example, in the digital twin, we expose just only schema validated JSON API, not raw data or free form data. So this reduce the leakage and inconsistent data in DECICE. After that, for the especially use case 3, robotics use cases, cloud robotics scenarios, we can apply security in a ROS2 robotic application, ROS2 layer for the robotic application. But we should consider that security is not free. It comes in a cost of the performance, accessibilities. So it's a kind of trade-offs. So with considering the security at the different layer, we are sure that in the DECICE that we have a robust and a secure data handling and the data protection situation in this project.
The KPIs we measure are designed to evaluate both the efficiency of the deployed algorithms and the performance of the DECICE infrastructure itself. And for example, some of these metrics focus on response latency. In particular, mission planning must generate a viable plan in under 1 minute to ensure disaster response is sufficiently fast. And other KPIs focuses on the resilience of the scheduling, and this means the ability of the scheduler to handle non-nominal scenarios, such as the loss of a drone due to adverse condition. In such cases, the workload previously assigned to that unit must be reallocated to another viable drone.
Yes, beyond the technical details, I would like to highlight two things that matter across the whole consortium, not just in just the University of Bologna. applied impact of the DECICE and collaboration and collaborative environment in the DECICE project. Applied impact, what we build is not just concept on the paper. We run it on the Kubernetes with the real telemetry data, time series storage, and ML modules. And we have a 3 use case scenario. We tested in a real use cases scenario the entire DECICE project. And also we have a very collaborative and good environment in DECICE. DECICE bring together 13 partners from universities and industry. The digital twin, AI scheduler, use cases, and many other subcomponents are developed through the cross work package collaboration. We use common data formats and interface, and we test on a shared test bed and shared repositories. This teamwork turn research into the functional tools. I'm grateful to all the colleagues across the consortium and in University of Bologna. And again, I want to thank you for the opportunity to present our work. Thank you.